All right, so yesterday we started talking about isomerism in a bit more detail. We said that isomers, as a broad classification, have the same molecular formula. However, we can group these into different subcategories, right? Constitutional isomers have different connectivity. Stereoisomers, on the other hand, have the same connectivity, but a different three-dimensional layout. Stereoisomers can even be subdivided further. So the first subdivision of stereoisomers are enantiomers. Those are two pairs of compounds, or a pair of compounds, I should say, where they're mirror images of one another, but they're not the same compound, right? So over here, I circled these ones to indicate that these are mirror images, but if you try to lay them on top of one another, they are not the same compound. Diastereomers, on the other hand, are not mirror images of one another. So not only are they not the same compound, but they're not mirror images on top of that. That makes them diastereomers. I did have one mistake I realized in my notes, and that was yesterday at the end of our lecture recording, or at the end of our lecture, I didn't put it online. We said if you assign stereochemistry for this stereocenter, this is an R, and then over here, this is an R. If we go over to its mirror image, what do you think the stereocenters are going to be in the mirror image? S and S. So what you might notice with enantiomers is each of those stereocenters will be the opposite, right? Because if it's a mirror image, they must be the opposite. So that's a nice clue you can use to find whether or not you've got a pair of enantiomers around, right? All right. So what I want to do is talk about this in a bit more detail, specifically regarding physical properties. All right, so constitutional isomers. What were those again? Different connectivity, right? So let's identify this. All right, so constitutional isomers have completely different connectivity. Do you think they're going to have the same physical properties or different physical properties? And by physical properties, that could be melting point, boiling point, things like that. Different, absolutely. All right, do you think it's going to be easy or difficult to separate out a mixture of constitutional isomers? Well, let's think about it, right? So let's say I've got this compound over here. That's ethanol versus something like this, where the oxygen is in the center. Which of these do you think has the higher boiling point? First one, why? Okay, so this one on the left can hydrogen bond. Therefore, we would predict that this would have a higher boiling point. This must have a lower boiling point. How can we separate things based on differences in boiling points? Distillation, right? So we did that in lab. So the reality is, with constitutional isomers, these are easy to separate. And an example would be something like distillation. There's other methods for purification, but distillation is just an example one that we're familiar with at this point in time. All right, so as a chemist, this is pretty nice if you have constitutional isomers. Not much work to purify your compound that you're interested in. All right, now let's jump to diastereomers. What were diastereomers again? How would we define them? Same connectivity. Are they mirror images? Okay, so let's mark that down. So same connectivity. Not mirror images. All right. These are actually kind of unique, right? They too have different physical properties. and they're going to be easy to separate. All right, so let's take an example of why this might be the case. So let's say I have this alkene with a fluorine here and a fluorine here versus this alkene over here. Are these mirror images of one another? No, not at all. All right, my question is, which of these will have the higher boiling point? Well, let's think about this, right? Let's think about the dipoles, right? This one will have an individual dipole going this way and this way. Is there a net dipole in this molecule? Okay, so no net dipole. What about the one over here? Yes, absolutely. The net dipole is going to be pointed way up in between the fluorines. So this one has a net dipole. Which one will have the higher boiling point then? The one on the right. So it makes sense, right? Diastereomers might have different dipoles, therefore we can separate them based on the difference in dipoles. So we can use that to our advantage. All right, let's think about enantiomers. All right, how do we define enantiomers? What are they again? They're the same connectivity, but what's unique about them? They're mirror images. But not identical. Another way of describing that is not superimposable. So sometimes I interchange between saying not identical or non-superimposable. All right, these get tricky. These have the same physical properties. These are really hard to purify. Okay, if they have the same physical properties, meaning the same boiling point, same melting point, same all of that stuff, how can we tell them apart? Everyone's like waving their fingers around. What do we call that? Optical rotation, right? The only way we can tell these apart is through optical rotation. That's what you meant? They rotate plane, polarized, light differently. i.e. in opposite directions. All right, what we'll do is we'll talk more about these purification techniques later, but as far as we're concerned, we're really not going to do any purification of enantiomers in our labs because they have the same physical properties. It requires a lot more nuance and critical thinking to actually accomplish that. Does that make sense? All right, so now what we're going to do is we're going to practice. Practice, practice, practice. All right, so what I'm going to do is I'm going to give you a formula. I want you to draw all of the potential isomers for the following compounds, meaning I want you to be as creative as possible, and I want you to determine which of the isomers are chiral or achiral, and then I want you to say, all right, if an isomer has a stereocenter designated as RS, and then determine the relationship between as many pairs of isomers as possible. All right, so we'll start off easy and we'll get harder. All right, my first example has 3 carbons, has 7 hydrogens, and a bromine. Somebody with a 3? All right, so let's try to go through and we'll just work through this. So one option is that we have 3 3 carbons with a bromine coming off the very end, right? Makes sense? All right, what about if I did bromine off the other end? You don't have to copy this down. This is the exact same thing, so why bother drawing it twice, right? So we don't need to draw it twice unless we want to. What's another option we could have? Bromine in the middle. Okay, so maybe I'll make that bromine a wedge off the middle, right? What about the differences between having the bromine as a wedge and a dash? Are these the same or are they different? I would say they're the same, right? If you flip one upside down, it's the same as the other. So I would say these are the same compounds. In addition, is there a stereocenter in here? No, there's not a stereocenter. If there's not a stereocenter, do we have to include dashes and wedges? Not really. You can if you want to, but it doesn't really matter whether or not you show dashes or wedges, right? So I'm just going to erase one of these and say, all right, we've got 2 of these. So I'd say this is it for these, right? No other possible isomers can be made. All right, second question. Which of these isomers are chiral or achiral? Let's pick this first one. Is this chiral or achiral? Achiral. There's not even a stereocenter. All right, what about this one over here? Is this chiral? No, there's not a stereocenter in it, right? So even though I drew a wedge, that doesn't mean that there's a stereocenter. So now we've got through our second bullet point. Third bullet point says if there's a stereocenter designated as R or S, I'll just say no stereocenter. In both. So we can't really label them an R or S in that situation, right? All right, so now my next question is what's the relationship between this compound and this compound? Constitutional isomers. Will these be easy to separate or difficult? Easy to separate, absolutely. All right, so now we're on a roll. Let's try it with our next compound. All right, this next one's going to be a little bit harder. C4H9Br. And in fact, let's kind of do this as a class because this one does get fairly complicated, right? All right, so now let's say we've got 4 carbons all in a line and we've got bromine coming off the end. We agree that's one of them? All right, what could another option be? Bromine in the middle. All right, so let's do it this way. 4 carbons, maybe bromine's coming off right here. Do we have a stereocenter in this? Yes. Where's our stereocenter? Must be right there. So what we could do is we could say maybe that bromine's a wedge, or conversely, maybe it's a dash. We agree on that? Okay. Let's try another one. What about if I do this? Well, let's think about this. Is this the same as one of the ones we've previously drawn? Well, let's think. Over here we go 1, 2, 3, 4. So that's 2-bromobutane, right? Over here it'd be 1, 2, 3, 4. That would also be 2-bromobutane. So we don't need to draw it again in this situation. So I'm just going to go ahead and erase that because it really doesn't need to be included. All right, let's try another one though. Maybe instead of moving the bromine around, maybe we move one of our carbons around. So maybe we move our carbon to a position. Let me clean this up. It looks like this. That still has 4 carbons off of it, right? So that would work well. All right, what about if we did, whoops. Like that. Let's think about this one again, right? Go 1, 2, 3, 4. See how that's still 2-bromobutane? We've already covered our 2-bromobutanes over here. What's going on then? What's the difference between these two and the one I've just shown? I just rotated a sigma bond, right? I didn't actually change the molecule, so we don't need to show this again. So I'm going to get rid of that there. That one doesn't really work. So now we've got to find another isomer that makes sense. The last one I can think of would look like this, right? Make sense so far? All right, so first question is determine which are chiral and achiral. So first one that I have drawn over here, is that chiral or achiral? Achiral, because it doesn't have stereocenters. What about this one right here? It's going to be chiral. It has a stereocenter and it doesn't have an internal plane of symmetry, right? Which is good. And then over here we know this one's kind of the same. Do the next two have stereocenters anywhere? No. So they must be achiral as well. All right, so we've done all of that. Now we need to designate R or S. So let's go over here and designate this one as an R or S. What do you think this one would be? See if you can do it in your head. It'd be R. And quickly we can check that and we'd say bromine is highest priority. This ethyl group will be second. This will be third. We rotate it around like this. That's going to the right. Where's our hydrogen? It's a dash and it's pointed behind us, so we would stick with our normal rules. Twist to the right is an R. All right. Conversely, what must this one be? It must be S, right? Because it's the opposite. All right. So we've got that done. Now we need to determine relationships. So what's the relationship between these? Constitutional isomers. What's the relationship between these? Enantiomers, absolutely. So these are enantiomers. What about between these two? Constitutional isomers. And we'll just do these two for fun. Constitutional isomers. Do we have any diastereomers in here? A pair of molecules that could be classified as diastereomers? We said diastereomers have the same connectivity, but they're not mirror images. Which of the compounds have the same connectivity? Yeah, the two chiral ones, we would say these have the same connectivity, but they couldn't possibly be diastereomers because we know they are, in fact, mirror images. So we don't have a pair of diastereomers here. So it does get a little tricky. All right, next one. It's going to be more challenging, and I want you to do this with your partner and see if you can figure out what's going on here. So 2-bromo, 3-chlorobutane. I'll give you a hint. There are 4. All right, so let's try to work through the structures just as a class, and then we'll try to answer all of the other questions next. So what I like to do with situations like this is ignore dashes and wedges at first, right? So what I've done is I've just drawn the bond line structure for 2-bromo, 3-chlorobutane, right? Easy enough. Okay, so now what we want to do is we want to figure out all of the possible isomers. Okay, so where are the stereocenters before we do that? 2 and 3, right? So that's kind of where we need to define things. So what I like to do when I'm drawing out all the options is I like to keep my carbon backbone a normal zigzag. All right, so the bromine, we get a pick. Do we want to make the bromine a dash or a wedge? You tell me. Dash. All right, that's good. We had consistency. All right, what about the chlorine? Oh, we'll do dash. All right, Next one, we'll do the same thing. Bromine this time. All right, wedge. Chlorine. Okay, we'll just do dash. All right. So first one we had a dash dash. Now we've got a wedge dash. What could we do the next one for bromine? We'll do a dash here for bromine, and then maybe a wedge for chlorine, right? Oops, sorry, that should be a chlorine. All right, what's the last one I'm missing? A wedge. So you see how we've already come up with all four combinations? All right, we know that we've got stereocenters off of all of these. In fact, I'm going to color code them. I'll do red here and green here. All right, my question for you is which of these are chiral and which are achiral? What do you think? I would say they're all chiral. Why couldn't they be achiral? There's no possible way to have an internal plane of symmetry in this, right? So it's impossible for there to be an internal plane of symmetry. So this would be chiral, 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 chiral. All right, let's focus on this red stereocenter. I'll in fact move my arrow to the other side. Is that R or S? It must be S, right? So we could go through and quickly assign that. That means that over here, this one must also be S. Make sense? All right. Let's think about what this one would be if it were a wedge. What do you think? It must be an R, right? Because we knew the dashes were S's. So we can quickly identify all of these after just assigning one of them, which is kind of nice. All right, let's do the green one. All right, is this chlorine? Or is the stereocenter where chlorine's attached going to be a dash? Or sorry, is the stereocenter where chlorine's attached going to be an R or an S? It's going to be an S. What about over here? S. What about over here? Must be an R. And then over here? Must be an R. Make sense so far? So if you're struggling to assign stereochemistry, it's okay to go back and assign priorities and double check everything, right? That's more than okay. Yep.
If there was like another carbon atom on the green one, the first one.
Mm-hmm. So the question was, if there's another carbon atom on the first one, would it be chiral or achiral? I would have to see the specific example. If you want to draw it out later, we can take a look at it. Yeah. All right, so now we've taken care of all of that. Let's identify relationships. What's the relationship between these two? They're connected the same way, so I don't think they'd be constitutional isomers. Bromine's always coming off of carbon 2, chlorine's always coming off of carbon 3. It's a little bit tricky. Are they mirror images? No. In fact, if we look at the stereocenters for the one where bromine's coming off, you see how they're flipped? So S and R, that is a mirror image, but the stereocenter in green is not flipped. It was S and S. So that means that these must be diastereomers. Do those have the same or different physical properties? Different. All right. What about these two? Tricky. Well, let's look at the red stereocenter. You see how the red stereocenter in one was R and then the other was S? So they're mirror images of one another. The green one in one is S and the other one's R. So they're also mirror images. So if they're both mirror images, what does that tell us? They're enantiomers. What about these two over here? These would be diastereomers. We could go through and identify other pairs, but I think we've done a pretty good job so far, right? Want to try an even harder one? You're like, no, but you're the teacher, so. All right. Next one. 2, 3, dibromobutane. Let's try to do this one as a class, kind of like we did the last one. So I'm going to do my zigzags for my butane backbone. Oops. And I like to keep them nice and consistent. That way we're only changing one thing at a time. And our bromines must be coming off of carbon 2 and carbon 3. Make sense? So in the first one, I'm just going to make this up. I'm going to say, all right, what if they're both wedges? Next one, I'll say, what if the one on the left is a wedge, and then this one's a dash? Then I'll say, all right, what if this one's a dash, and this one's a wedge? Then I'll say, all right, what about a dash and a dash? A little bit tricky here. Do we all kind of agree on the 4 possible options here? Similar as what we had before. All right, let's mark our stereo centers. So I've got stereo centers here, 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 and here. So I've labeled all of those. All right, let's just try to assign stereochemistry really quick. What's the stereochemistry for that one? It would be R. Which means that this one must be what? It must also be R. What about this one? It must be flipped, right? Because now it's a dash. What about this one? S as well, right? So once you assign one, it's pretty quick to assign the rest, as long as you're keeping everything else the same, right? Let's do the same thing over here. Be R. What would this one be? S. What about this one? R, because it's the same as our original, it's a wedge. All right, and then what about over here? S. All right, so now we've got to determine a few things. First one, I'm just going to jump into this. What's the relationship between these two? Diastereomers, why? Yeah, so if we look at carbon 2, you see how it was R and R? That was not flipped, meaning they're not mirror images. But over here, we did flip R to S. So we can tell not all of this is a mirror image, right? Only a portion of it is. So immediately we can go through and we can say, all right, these are diastereomers. All right, let's do the next one. So you're saying enantiomers. This is tricky. Here's what I'm going to do. I'm going to draw this down here again. Just redraw it. Do we agree that's the same molecule, just redrawn in green? All right. What I'm going to do next. So I'm going to rotate this sigma bond. I'm going to say, all right, if I rotate that sigma bond, it's going to look like that, right? So up here, we said that this is going to be an R, and this is going to be an S. Over on the left, this is still an R, and this is still an S. You can check, right? So we didn't change the molecule. All we did was rotate a sigma bond, which is perfectly allowable. We saw that in Newman projections. Does anybody notice anything unique about it when it looks like this? It's symmetrical, right? So if we cut this in half, one side is the same as the other side. Does everyone see that? What does that mean? It must be achiral. So let's even go ahead and write that up here. So first one would be chiral. This one would be achiral. All right. So if we have an achiral compound, will it ever have a mirror image that is different than itself? It's kind of a weird thing to think about, right? Only chiral compounds can have enantiomers. So in this case, let's go back to our original question. What's the relationship between these? They're identical, which is a bit weird to think about. If you actually build this with your model kit and try to overlay them atom for atom, they're exactly the same thing. Even though they are mirror images of each other, sometimes you have mirror images that are just the same thing because they're achiral. It's weird to think about. And let's make a note here. So molecules with internal mirror planes do not have enantiomers. It's kind of tricky to spot, right? But down here we said that these compounds have internal mirror planes. All right, last but not least, what about these two? Diastereomers? All right, let's keep on going, just for fun. Let's do the first and last ones here. What's the relationship between the first and the last ones? What do you think? So let's do this down here. The big question, right, is are we going to run into a similar situation where they're identical? So let's do the same thing, but this time I'm going to do this one in, let's do purple. So, whoops. So I'm just going to copy this down here in purple. And we're going to do a sigma bond rotation like this. Does this have an internal mirror plane? No. So that means that it's chiral. Can chiral compounds have enantiomers? Yes, they can. So in this last example up here, these must be enantiomers, because there's no internal mirror plane. All right, so just to finish it off, this third one right here, is that chiral or achiral? Keep that in mind. Don't overthink it. We said they're identical, right? So if they're identical, will that third one be achiral or chiral? Achiral. What about the last one? Must be chiral. All right, so how many total isomers do we have for 2,3-dibromobutane? Only 3, right? Even though we drew 4, 2 of the 4 were identical. So we could draw 4, but it's just kind of wasting our time. Sometimes you have to draw them out, though, before you can spot those identical matches. All right, I've got a term I need to throw at you. And this is a meso compound. All right? So a meso compound are compounds, oops, not compounds with stereocenters but also an internal mirror plane. This has 2 important things we need to consider. First thing is, will meso compounds ever be chiral? No, if they have an internal mirror plane, they'll never be chiral. All right, second thing is, do meso compounds ever have enantiomers? No, because they're achiral. Only chiral compounds can have enantiomers. Oops. Sorry, that should be achiral with no space. And will these rotate plane polarized light? No. So we could write not optically active. All right, so that's the big takeaway with meso compounds. We ran into a meso compound during that last example, right? Is it always easy to spot meso compounds? No, sometimes you need to rotate sigma bonds in order to spot them. All right, so there's a handful of tricks that I think we have time to get through. And these tricks will hopefully make your life easier. So enantiomers. It's a pair of compounds, and I'm going to abbreviate compounds, where all of your stereocenters are flipped. But connectivity is the same. And I'm going to put an asterisk here. What do you think that asterisk is likely going to be talking about? Meso compounds, right? If you've got an internal mirror plane, we said we will never ever run into enantiomers. All right, next one is diastereomers. You can probably tell by my underline in the example above that it's going to be what? It's going to be a pair of compounds where all of them are flipped? No, only some of them, right? All right, and then last but not least, we've got meso. Okay, a meso compound is a compound with more than one stereocenter but what's going on in a meso compound? How can we spot them? But there's a mirror plane, right? All right, my hint with meso compounds, and I'm going to put this asterisk up here because we said watch out for that when you're comparing enantiomers. My hint is that the stereocenters on one side of the mirror plane must be opposite of the stereocenter on the other side. Does that make sense? So if there's a mirror plane where you're cutting the molecule in half and you've got a left-hand side and right-hand side and you've got an R on your left-hand side, what must it be on your right-hand side? S. It must be the opposite. So you can use these as a pretty easy trick. So if you're ever stuck identifying what's going on here? Just assign stereochemistry to specific groups, right? And then look, have they been flipped? If so, what's the relationship between the flipping? You can pretty quickly determine what's going on in these situations. Does that make sense? I will say the pod is a little bit tricky. One thing I'll recommend on the pod is use your model kit, especially if you're having trouble interconverting between Newman projections and the 2D bond line conformation.